Right, let's have a look at this then. So the first part of the question asks you to calculate two angles. This one here, theta, and this one here, which is phi, right? So to calculate theta, we are looking at what happens at this boundary, right? So this is the incident ray, this is the refracted ray, okay? The light is going from air into the core. Remember, this is the core and this is the cladding, okay? So N1, which is air, is 1, and N2, which is the core, is 1.63, okay? Then theta 1, which is the angle of incidence, is 21.2 degrees, and in this case we're looking for theta, which would be theta 2, okay? So using a Snell's law equation, we have N1 sine theta 1 equals N2 sine theta 2, and we want to find theta 2. So rearranging that, sine theta 2 equals N1 over N2 times sine theta 1. Okay, which is 1 over 1.63 times sine 21.2. Okay, so if you work that out, 1 divided by 1.63 times sine 21.2 is 0.22. Okay, now that's not theta 2, that is sine theta 2. So theta 2 is sine to the minus 1 of 0.22. Okay, what I think I might do is I might do that all again so that I'm not rounding. So shift sine to the minus 1 of 1 divided by 1.63 times sine 21.2, and that is 12.8. Alright, so theta 1 is 12.8 degrees. Alright, okay, now we need to find this angle down here, don't we? So let's just have a look. This is geometry again. That's a horizontal line, yeah, which is parallel with the edge with these boundaries. So what have we got going on? Let me draw a normal here. So if that angle there is 12.8, then this angle must also be 12.8, and this angle must also be 12.8, and this angle must also be 12.8, right? Now if that in total is a right angle, yeah, then phi equals 90 minus 12.8, which is 77.2 degrees. Okay, so those are our two angles. Right, now the question says, explain why light transmitted at this angle will not undergo total internal reflection. Why will light transmitted at this angle not undergo So let's work out what the critical angle is first, right? critical angle equation, which you need to be able to derive. I'm going to just write it down for now. Sine theta c equals n2 over n1. So we're looking at we're looking at this boundary, okay, where n1 is the core and n2 is the cladding. I know they call them 2 and 3 here, but this is the more dense material, the core. This is the less dense. So let's just make a note of that. N1 for this is 1.63 and N2 is 1.60. The core and the cladding. Okay. So sine of the critical angle is 1.6 or 1.60 over 1.63. Okay, so the critical angle is sine to the minus 1 of 1.60 over 1.63, and that is shift sine to the minus 1, 1.60 divided by 1.63. There you go. So the critical angle is 78.9, let's round it up, 79 degrees. Okay, so why were light transmitted at this angle not undergo total internal reflection? Because the angle of incidence is less than the critical angle. Okay. Last of all, we've got a ray that does undergo total internal reflection. Right, a ray that does undergo total internal reflection. We've got an angle here shown to be 5 degrees. Now this is tricky, and this is about multi-mode dispersion. Okay. Calculate the extra distance that this light ray travels compared with light that travels straight. So if the light was going straight, it would be, you know, when we looked at it on the slides, it would be going that pathway, right? Now it says here that the horizontal distance, so if it was going straight through the middle, it will be travelling 14 kilometres, right? But our ray of light is not doing 14 kilometres. It's taking this path, right? So if we just look, let's just look at this triangle here, right? Because instead of travelling that distance, our ray is travelling that distance. And this is all to do with the right angle triangle geometry. We can work out what that length is and compare it with the, you know, what multiplies up to the 14 kilometres. Right, so let me draw a right angle triangle where that's 5 degrees, where this is 14 kilometres. I know it isn't 14 kilometres, but the ratios with this triangle will work for the entire longer distance and the entire straight through. So let's find out what that new line, what that new path is, right? Look at it. We've got an angle, we've got an adjacent side, and we've got a hypotenuse. So you should see that cos of that angle equals adjacent over hypotenuse. Right, let's work out what x is. Rearranging that will give us x equals 14.0 over cos 5 degrees, and that is 14.0 divided by cos 5 is 14.0, let's put a few, 14.053 kilometres. Okay, so can you see that that is a greater distance than that? Yeah, what's that extra distance? That extra distance is this. Take away the 14, so it's 0.053 kilometres. Okay, so that infrared light is travelling at the same speed as that infrared light. Yeah, if it's travelling at the same speed, but it is travelling a greater distance, then the time it takes is going to be different, right? This ray is going to take longer to come out the other end of the fibre than if it went straight through the centre. And what is that time? So let's have a little look. So that extra distance takes time t, and if we rearrange this, t is distance over speed, and I best put this back into SI, into meters, SI units. I'm going to divide by the speed of light, which is 3 times 10 to the 8, and that gives me, this is quite a small amount of time, but when you're sending data, oh hang on, 0.053 times 10 to the 3 divided by 3 times 10 to the 8, 1 point, let's round it, 1.8 times 10 to the minus 7 seconds. Yeah, however, that extra time means that the signal, this signal arrives that fraction of a second later than the signal that goes through the shortest path, and any other refracted rays are going to arrive at a different time. Okay, so those time differences will cause like an overlap or a blurring of the output, and that literally is multi-mode dispersion. Okay, so this extra time means that light taking this zigzag path arrives later than light that travels straight through the shortest path. I'm going to smooth this up a bit. Okay, and any other paths also take longer. Okay, so that means then this causes an overlap or like a blurring of the output, which equals multi-mode dispersion. Okay.